Welcome to this video on magnetic effects of current. The magnetic effect was first discovered by a German physicist called Oersted. He did this famous experiment in which a current was passed in a wire, and it was observed that there was a magnetic needle was getting deflected due to the current carrying conductor. And as direction of the current was reversed, it was observed that the direction of deflection changed in the magnetic compass. So this was the first time someone discovered the magnetic effect of current. If you have a straight current carrying conductor, and if you move your magnetic compass, you will see that the needle of the compass, it moves in circles, and that kind of gives us the direction of the so-called magnetic field lines, which is nothing but the path traced by the compass. So this is the path traced by the compass for a current carrying conductor I. This direction of this magnetic field for a current I can be found using the right hand corkscrew rule. So if your thumb is pointing to the direction of the current, and your fingers your fingers give you the direction of the magnetic field. In the same way, if the current is downward, then the loop of the finger gives you the sense of the magnetic field. So that's how you can find out the direction of the magnetic field. And usually the magnetic field is denoted by B. So here you have, if the current is in this direction, then the magnetic field is given by this loops. Right? An extension to this would be a circular loop. So if you have a circular loop, and if you have the current flowing in this direction and coming out in this direction, then you can imagine that over here there would be a small section of conductor, and that conductor would result in magnetic field in loops, the same as the one we see here. And here the current is coming back, so here again there will be loop of magnetic field, and this loop would be responsible for the magnetic field in this direction. But what you can see is in the center, either ways the magnetic fields are adding up, and all the magnetic field lines are going into the coil. So we say that the magnetic field in the center is the net magnetic field is going inward. In other words, the direction of in and out is denoted by with the help of an arrow. If you imagine an arrow going inward, you'd be seeing the tail. So, and if you have an arrow that's coming out, you would be seeing the tip of the arrow. So this is representing out, and this represents in our three-dimensional space. In as in into the monitor or screen you're looking at. So here the net effect of B is going inward. And if you see the tail, that means that you're looking at south, and if you're looking at the head, then that means that you're looking at the north. So the tail is the south, and the head is the north. So here in this particular case, since you see the tail, this is a south side. This side is the south side of the coil of the magnet, of the magnetism. So we say this is your south side. Now what it means is that if I bring a compass near this face of this coil, the north face of this magnetic compass would point towards the center, right? That's what it means, that it attracts the north side of the compass. And the other side, though, would be the other side of the coil. When you view from the other side, you will see that the field lines are coming out straight. So you will see from the other side, you will see magnetic field like this. So let's see what do we see from the other side. So of course, when you look at it from the other side, you will see that this loop is carrying current through the, such that it goes in like this, and here it's like that. So if you draw the loops on both this, the magnetic loop, you will find that the magnetic field is in this direction, right? Which is given by your right hand rule. So that's a current is going here, and then your magnetic field like this. So that's what you would find. And on the right hand side, your magnetic field lines would be like this. So you will see that magnetic field lines are coming out. So from this side, if you put a compass, you will see that your south side of your compass would be facing the north face of the coil. So this is what we call as a north face of the coil. As you can see, this arrow of this N and this arrow coincides. So this is the north side of the coil. Moving further, for a solenoid is a set of coils which carries current. So if all the currents are, let's say it's moving up, and you try to trace the path of a compass, you will observe that the compass moves exactly just like a bar magnet. So the field lines are such that the compass would point like that, and the compass would point like this. So this kind of tells you that this side is your north, and this side is your south of the solenoid. You could also apply the previous rule that we talked about here, that if your current is going clockwise, and if you view from here, your current is moving. Your current is moving in anti-clockwise, just like this. So if you view from here, it would be analogous to this side. So the current is moving anti-clockwise, and you're facing the north. And here, all these coils will add up the magnetic field over here, right? And if you're looking at here, your current is moving clockwise, just like this case A, and you're seeing at the south side of the solenoid. So for all practical purposes, the solenoid behaves just like your bar magnet. The magnetic field lines are represented just like your bar magnet. And what that means is the magnetic compass moves exactly the same way as it would move in a bar magnet, in a solenoid. Except for the fact that if you keep magnetic compass in the center of the bar magnet, it would point like this, which is the needle will point towards the south. However, in a magnetic field, in a solenoid, in the center would be slightly different. It would continue to point in this way. That is, a magnetic compass would the magnetic field lines would continue to be represented like this. It would kind of go like that, right? So that's magnetic field lines inside the solenoid. In the next video, we will talk about electromagnets. I hope you enjoy this video. See you in the next one.